Welcome to the Sensor-to-Image GigE Vision IP Core Training. This course provides a general overview of the GigE Vision protocol. This course explains what GigE Vision is in general, and gives an overview of the history and different versions of the protocol. Focuses on explaining the key features and concepts of the GigE Vision protocol. But what actually is GigE Vision? GigE Vision is a camera interface standard, which is developed and maintained by a group of machine vision companies, including Sensor-to-Image. The ownership and management of the standard is handled by the USA-based Association for Advancing Automation, or in short, A3. Ethernet as transport medium became interesting for the vision industry with the availability of 1 gigabit and now 10 gigabit equipment, as they provide sufficient data bandwidth capacity to allow large uncompressed video streaming. Cable length is also an interesting benefit and is specified up to 100 meters over copper, and much longer over fiber optic cables. GigE Vision is based on the UDP protocol with some security add-ons defined by the standard to provide reliability. The net speed, or data bandwidth, of a GigE Vision connection is about 115 megabytes per second for a 1G link, and 1100 megabytes per second for a 10G link. GigE Vision doesn't require special hardware. Therefore standard cables and network cards can be used, which keeps the overall cost low. As GigE Vision is based on standard Ethernet, it can benefit from its flexibility. This enables networking flexibility to set up point-to-point or point-to-multipoint, also known as multicast, connections. Bandwidth requirements are increasing as image sensors provide higher resolutions and faster frame rates, so GigE Vision can also benefit from the evolution of Ethernet. The next big step in this progression will be to adopt technologies to achieve 25G and 100G bandwidth. How did GigE Vision evolve over time? The first version was released in 2006, followed by 2 versions in 2009. Version 1.2 is still widely used. The main new features introduced included action commands, a mechanism which can be used to trigger cameras. Version 1.2 extended the type of GigE Vision devices by including receivers, which for example could be an FPGA-based design which operates GigE Vision cameras and receives the stream data for further processing, such as what is seen in embedded vision systems. Further, the concept of non-streaming devices that do not have a stream channel, for example high-speed image, and are used, for example, for light controllers operated over a network. Version 2.0 formally introduced support for 10G speed, although GigE Vision is speed agnostic. It also added link aggregation as an additional way to increase throughput. IEEE 1588, also known as Precision Time Protocol, or PTP, was also included to allow precise synchronization and triggering of several cameras in the network. During this time, the major version changed as there were also some extensions to the streaming protocol that were not able to be made backward compatible. Version 2.1 was released in 2018, which included introduction of a new payload format. For complex datasets used for example in 3D cameras, the multi-part type was added, for example for such cameras to transmit visible 2D image data as well as the associated 3D point cloud, or even for LiDAR-ing visible images of the same scene. The current, latest, released version is 2.2, which introduced the GenICam payload type. This is an even more flexible data container than multipart, and it is also used in other transport layers like CXP and USB 3 Vision. The next upcoming GigE Vision 3.0 version will be significant. It will again be changing the streaming format of GigE Vision. This is necessary as the existing UDP-based streaming protocol cannot be handled efficiently on host computers at data rates above 10 gigabits per second. The remote DMA protocol RoCE v2 will be adapted to GigE Vision to overcome these limitations. Let's have a closer look at the key features and concepts of GigE Vision. These include discovery mechanism to find GigE Vision devices in the network, a channel concept to exchange different kinds of information between device and host, the control protocol to exchange control information, the streaming protocol to send stream data, for example images, from a camera to a host application, the message protocol to send events from a device to a host application, and finally, The connection to the GenICam software standard. Please use the official GigE Vision specification as reference. Important chapters are listed on the following slides. The specification is available via the A3 website. The discovery phase consists of 3 steps. First phase is the link negotiation, which is typically performed at the hardware level between PHYs. Once the link is established, the network devices have to configure each of their IP settings. Standard mechanisms such as static IP address, DHCP or link local address assignment are used for this step. When a GigE Vision device has finished these steps, it is ready to be connected to a control application. For that, an enumeration process is executed. The device listens for discovery messages on the GigE Vision control port, UDP 3956. When receiving such a discovery message, the device builds and sends the discovery acknowledge packet, which includes basic information about the device like manufacturer, model and MAC address. With these data, an application can build a list with all available GigE Vision devices and a user can open the device for further operations. To exchange different types of information between the GigE Vision application and the GigE Vision device, the GigE Vision standard introduces 3 types of communication channels. The control channel is used to configure a device. For example, that could be a command to read or write the exposure time of a camera. The transaction is initiated by the host and acknowledged by the device. There must always be one control channel available. The stream channel is used to transfer image data or other data from the device to the host. This is a unidirectional communication, initiated through the control channel. The typical number of stream channels is 1, but there might be 0 for a non-streaming device, or more stream channels for special applications. The message channel is similar to the control channel, but in this case the device is initiating the transaction by sending asynchronously an event. The host can acknowledge it when requested. The message channel is optional, however more than one is not allowed. Let's have a closer look at these channels, and respectively the protocols used therein. The control channel uses the control protocol to exchange command and acknowledge messages between a GigE Vision device and a GigE Vision application. This protocol implements functions to read or write device registers and to read or write memory of a device. It is also used to instantiate a stream channel so that it can be used also from the device to send events over the message channel. Each command has a request ID, which is a mechanism that allows the system to identify data loss in the transmission and to resend commands or acknowledge packets in case of a communication/transmission error. The stream channel uses the streaming protocol to transfer data from the device to a stream channel receiver, typically a PC application. The protocol defines 3 types of packets, each containing different types of information. Their purpose is to ensure that the stream channel is self-describing. The leader packet contains information about the following data, for example it specifies the dimensions of an image and the pixel coding. The payload packets contain the actual payload, so for example the pixel information of an image. The trailer is the last packet of a block and may provide updated information about the block. Each packet has a packet ID, so that the receiver knows how to handle it and how to calculate the destination address of a received buffer. The packets are sent in order and when there are special network topologies are also received in order. As the streaming protocol GVSP is based on UDP, this is a send and forget approach. This means the camera doesn't know and doesn't care if the packet was received properly by the GigE Vision application. Dependent on the host PC's configuration, it might be possible that packets get lost between network card driver and user buffer. Thanks to the packet ID, the application can detect a missing packet and can ask the camera to resend it with the packet resend command. But beware, this mechanism works fine for occasional packet loss, but it doesn't fix general network or configuration problems. That means the baseline for the streaming should be 0 packet loss. The packet resend is only an additional method to increase reliability. The data considered for streaming is structured as a block. The GigE Vision standard specifies some payload types to characterize the content of the payload. Image payload type is the most important type and typically contains 2D image data, optionally with additional chunk data. The detailed specification of the block is available in the leader packet, where block-specific information is provided. In the case of image payload type, these include such things as a timestamp, the pixel format, width and height and offset information. These fields vary depending on the payload type. The payload packet uses the same block ID field as the leader and trailer. It also includes a packet ID field and of course the payload. The trailer packet may update the size_y field of the leader, which is used when dynamic image sizes are used. The message channel is a way for a GigE Vision device to send messages to an application without being asked. Technically, the message channel also uses the GigE Vision control protocol, but the transaction is initiated by the device, not the application. So the information flow is that the device sends a message. You can think of this as an event to an application. The application receives and processes the message. The application sends an acknowledge if requested by the device. A typical use case for events is a monitoring process on the camera, which sends a message when a parameter exceeds its limits. GigE Vision is not an isolated standard, it refers to the GenICam standard. GenICam is a generic programming interface for any type of camera, so not only for GigE Vision cameras. All major interface standards like CoExpress, USB 3 Vision or Camera Link rely on GenICam. GigE Vision devices use GenICam to advertise the device's capabilities. For this to work, a device is required to have an XML file, following the syntax of the GenICam GenAPI module. This XML file should use the standard feature naming convention, SFNC, which is another part of the GenICam standard. This SFNC defines a consistent way for different camera vendors to describe their features, which provides a universal understanding of feature names and how they work on cameras. That helps to increase interoperability of software with devices of different vendors. GigE Vision devices also have to follow the pixel format naming convention, which defines the coding of different pixel types. For further information, please obtain and refer to the full GenICam specification, which can be found at genicam.org. GigE Vision is a powerful and well-established interface for vision devices. GigE Vision uses standard Ethernet components and protocols. GigE Vision supports transfer rates from 100 megabit per second up to around 10 gigabit per second. GigE Vision is evolving to cope with new requirements regarding more complex data structures and higher bandwidth.